The last question on tutorial sheet 2, question 8. A carrier of 5 volts RMS and frequency 1 MHz is added to a modulating signal of 2 volts RMS and frequency 1 kHz. The composite signal is applied to a biased diode rectifier in which the relationship between current and voltage over the range plus or minus 10 volts is given by an equation that I'll write down in a moment. So we need to take out the information that we know from the question. So first of all, it says a carrier, so we have some carrier voltage VC. Well, it's got 5 volts RMS, so we can write that as 5 times the square root of 2. So that is now we've converted from RMS to peak by multiplying by the square root of 2. We're not told whether it's a sine or a cosine, and as I've said at various points in the lectures, it doesn't actually matter. I'm going to call this a sine wave. And in this case we have 2 pi times 10 to the 6 t, because the question said that we had a 1 megahertz carrier frequency. In other words, Fc is equal to 1 megahertz. And then we have a message signal, a modulating signal of 2 volts RMS. So we've got 2 root 2 sine 2 pi times 10 to the 3 t. In this case, Fm is equal to 1 kilohertz. So those are the 2 bits of information that we have. We've got 2 signals, and those are, the important word is they're added together. So what we are doing in essence, if we think about it as a circuit, we've got 2 signals that are going in to our system, one which is VC and one which is VM. So the total voltage is Vm plus Vc, and that is generating a current I, and that current is given by the equation in the question, which is equal to 5 plus V plus 0.05 V squared microamps. So we need to know this is the total voltage that's applied to our system. So if we do that, we have to work out this equation and expand it fully. So what we have is I is equal to, 5 plus, the total voltage, which is just Vc plus Vm. So we have 5 root 2 sine 2 pi, I'll simplify this to Fct, plus 2 root 2 sine of 2 pi Fmt. So that's the total voltage, which is simply the sum of these 2 voltages. Then we've got to do the squared element. We've got 0.05. If we do the squaring of Vc plus Vm, we get 50 sine squared 2 pi Fct plus 40 sine 2 pi Fmt multiplied by sine 2 pi Fct plus 8 sine squared 2 pi Fmt. Okay, so that's the full equation. So we've applied the total voltage into this equation, and this is what we've derived at this point. Now at this point, what we're trying to do is from this equation we're trying to create an AM signal, and of course our standard form for AM equal to VC 1 plus M sine omega MT sine omega CT. So we're trying to extract the elements from this equation that look like this. And if we do that, what we're trying to do is find a VC times sine omega C of t. Well, if we look in here, well, this part of the equation is at the frequency of FC, so that matches with this bit. So what we've got is 5 root 2 sine 2 pi FC of t and then we need to pull out the bit that has got a multiplication of sine omega C of t and sine omega M of t. So if we expand this equation, we're going to get that multiplied together. And if we look in the equation, this occurs here, which is the 40 sine 2 pi FMT sine 2 pi FCT. Don't forget, it's also multiplied out by 0.05. If we do that, and apply that to the standard form, we get 1 plus root 2 over 5 sine 2 pi FMT. So that's just extracting the information that we need from this long equation so that it looks like the standard form of an AM signal. At this point, we can compare that equation against this equation to work out part A of the question, which is simply asking for what is the modulation index. So we know the modulation index is the thing that comes before the sine, which is M there. So M in this case is very simply root 2 over 5. And if you work that out as a percentage, or got 28.2% or 0.282. So that's part A. Part B requires knowledge of all the components in that circuit. So if I redraw the circuit again, so we're still applying our VC plus VM signals in at this point, and of course we had the equation for the current, which was quite long. If I just show you, so it's this equation that we're interested in, and we've got to extract the different frequency components from each element of this equation. So if I write down that equation again so that we can keep track of things, so we've got 5 plus 5 root 2, and I'll simplify this to omega C of t, plus 2 root 2 omega M of t, plus 0.05 times 50 sine squared omega C of t, plus 40 omega C of t sine omega M of t, plus 8 sine squared omega M of t. So we've got to track what frequency components there are. So if we look at these individually, well, first of all, we've got 5. Well, that doesn't have any frequency dependence associated with it, so that is a DC component. So we have a component that's at DC. Then we move on to the next component. Well, that's just purely at a frequency of omega C. and then we have a component at omega m. And so hopefully that's relatively simple for that element of the equation. Then we've got to look at what happens here. Now when we use a trigonometric identity which says sine squared of a, that is equal to a half of 1 minus cos 2a. In other words, when you square a sine wave, you create a DC component and a component which is at twice the frequency. So we're going to create a component which is at 2 omega c. We're also going to create a component, because we've got a sine squared omega m of t, at 2 omega m. And then we've got the components associated with sine omega c of t and sine omega m of t. And when we multiply two different sine waves of two different frequencies, we get a sum and a difference. So the sum is going to be omega m plus omega c, and we're going to get omega c minus omega m. If we work that out in actual rather than angular frequencies, we work it out as in hertz. Obviously that's going to be 0 hertz. Omega c, well that's going to be 1 megahertz. Omega m is 1 kilohertz. 2 omega c is 2 megahertz. 2 omega m is 2 kilohertz. And then you've got the sum, which is going to be 1.001 megahertz, and the difference is 0.999 megahertz.